In further mathematics, we study differential equations, which describe how a quantity changes. A first-order differential equation sometimes cannot be integrated directly, so we multiply every term by a special multiplier called an integrating factor, and this makes the left-hand side become the derivative of a simple product. A second-order differential equation with constant coefficients is solved in two parts. First, we find the complementary function, and then, if the equation has a right-hand side that is not zero, we also find a particular integral. Let us work through an example using an integrating factor. We want to solve the derivative of y with respect to x plus 2 divided by x times y equals x for x greater than 0 in symbols, that is dy by dx plus open bracket 2 divided by x close bracket times y equals x. First, we identify the coefficient multiplying y, and we call it p of x. Here, p of x equals 2 divided by x. The integrating factor is found by raising e to the power of the integral of p of x with respect to x. In symbols, the integrating factor equals e to the power of integral of 2 divided by x dx. The integral of 2 divided by x dx equals 2 times the natural log of x. So the integrating factor equals e to the power of 2 times the natural log of x, which simplifies to x squared. Now we multiply every term in the original equation by x squared. The left-hand side becomes the derivative of x squared times y with respect to x, and the right-hand side becomes x cubed. Next, we integrate both sides with respect to x. This gives x squared times y equals x to the fourth divided by 4 plus a constant, which we call c. Finally, we divide through by x squared to get y by itself. This gives y equals x squared divided by 4 plus c divided by x squared. If we plot this family of solutions for different values of c, we see a set of curves in the xy plane, each one shifted up or down depending on the constant c. We can also picture this as a three-dimensional surface by treating c as a third axis alongside x and y. As we slide along the c-axis, each slice of the surface gives one of the two-dimensional curves we just saw, showing how the whole family connects together. To check our answer, we differentiate y equals x squared divided by 4 plus c divided by x squared with respect to x. This gives dy by dx equals x divided by 2 minus 2 times c divided by x cubed. Substituting this back into the left-hand side of the original equation, we get x divided by 2 minus 2 times c divided by x cubed plus 2 divided by x times open bracket x squared divided by 4 plus c divided by x squared close bracket. Multiplying out the bracket, the 2 divided by x term gives x divided by 2 plus 2 times c divided by x cubed. Adding everything together, the 2 times c divided by x cubed terms cancel, and the 2x divided by 2 terms combine to give x. Since this matches the right-hand side of the original equation, which was simply x, our solution is confirmed to be correct. So the general solution to this differential equation is y equals x squared divided by 4 plus c divided by x squared, found using the integrating factor method.